In the late 1960s, Chevrolet believed it had complete control over performance. The factory decided what engines lived, what engines were limited, and how much power the public was allowed to have. But in a quiet California garage, that authority was quietly dismantled. With no corporate budget, no secret factory access, and barely $35 in parts, a teenage hot rodder exposed a flaw in Chevrolet's own engineering strategy. What followed wasn't just an embarrassing loss at stoplights, it was a lesson Detroit couldn't ignore. This story isn't about cheating the system. It's about understanding it better than the people who built it. The corporate stranglehold on speed. In 1955, Chevrolet released a piece of engineering so perfect it arguably became the most important V8 in history. The small block architecture was a masterpiece of modularity, built on a 4.400-inch bore center that turned the engine bay into a literal Lego set. This consistency meant that as displacements grew, the fundamental DNA remained the same. By 1962, the 327 cubic inch variant had arrived, cementing itself as the gold standard for performance. With its high-flow cylinder heads and aggressive personality, the 327 was the heart of the Corvette and the king of the street. But by 1967, the landscape changed. Chevrolet introduced the 350 cubic inch block to handle the weight of increasingly heavy American steel. On paper, it was a triumph of torque, featuring a longer 3.48-inch stroke that promised more power than ever before. However, the reality inside the engine was a corporate betrayal. General Motors, fearing for engine longevity and wanting to ensure compatibility with low-grade fuels, intentionally neutered their new powerhouse. Instead of equipping the 350 with high-performance components, they choked it with massive 76cc combustion chambers. This design choice capped the static compression ratio at a lazy 9:1. While the 327 had been a high-strung athlete, the factory 350 was an efficiency disaster, leaving massive amounts of thermal energy on the table. Detroit's engineers had built a giant, then effectively tied its hands behind its back for the sake of the average commuter. For the racers in Southern California, this was an insult. They saw a displacement gap that should have been a performance revolution, but was instead a missed opportunity. This corporate compromise created a massive efficiency gap, waiting for someone brave enough to ignore the factory manuals and exploit the modularity of the small block. The making of a mechanical maverick. The technical insight required to humiliate General Motors' engineering department did not come from a university lecture hall. It was forged in the heat of Phoenix, Arizona, and refined in the dirt floor garages of the post-war West. Born in 1930, Bruce Crowder was a boy obsessed with the physics of motion. By the time he was 13, he was already tearing into a tiny 5/8 horsepower Briggs & Stratton engine mounted on a moto scoot. Most kids were happy if their bike just ran, but Crowder was already treating the low-output platform like a laboratory, obsessing over how to extract every possible ounce of velocity from a displacement barely larger than a lawnmower. By age 17, his ambitions grew alongside his engine displacement. He graduated to an 80 cubic inch Harley Davidson, but he did not just ride it, he hacked it. He began experimenting with raising the compression ratio, a move that achieved the rare double victory of increasing top speed while simultaneously improving fuel economy. This period established the core of the Crowder philosophy. He moved to California in 1950, landing at the epicenter of the hot rodding boom and working under industry titans like Paul Schaefer. There, he spent his days machining flywheels and fabricating exhaust flanges for the first generation of overhead valve V8S Crowder, became known as the thinking man's racer because he viewed every piece of cast iron as a math problem rather than just a hunk of metal. He was a grinder with dirt under his fingernails who possessed the rare ability to see the untapped thermal potential that professional engineers had overlooked or ignored. The math of mechanical superiority. In 1969, the barrier to entry for serious performance was a wall of cash. Aftermarket aluminum heads were the dream, but for a young mechanic working on a shoestring budget, they were a financial impossibility. Bruce Crowder looked past the glossy catalogs and focused on the salvage yard. He realized that the modular architecture of the small block Chevy held a secret. The high-performance 64cc heads from an older 327, known as the double humps or camel humps, shared the exact same bolt pattern as the neutered 350 blocks. This was the catalyst for an absolute assault on physics. He was effectively shrinking the room the air-fuel mixture had to hide in. This single change rocketed the compression from a conservative 9.1 to a street-lethal 11.1. In the world of engine building, every full point of compression added generally yields a 3 to 4% increase in power. Crower was gaining nearly 30 horsepower before he even touched the intake or the camshaft. But the real magic happened in the intake ports. While the factory 350 heads had larger, lazier runners, the 327 double humps utilized smaller ports designed for high intake velocity. This created a powerful ram effect. As the intake valve slammed shut, the sheer kinetic energy of the high-speed air column packed extra oxygen into the cylinder. SIG. The Junkie SAR giant killer results. The numbers produced by Bruce Crower's hybrid engine were so staggering they bordered on the impossible for a street-built motor in 1969. By investing a mere $40 in salvaged cylinder heads, Crower had assembled a power plant that generated 510 horsepower and 465 pound-feet of torque. To put that into perspective, the standard 350 V8 of the era was wheezing out approximately 300 horsepower. Even the most aggressive factory performance options, which cost significantly more at the dealership, topped out around 350 horsepower. Crower had effectively bought 200 extra horsepower for the price of a steak dinner. This was not a marginal gain or a subtle improvement in drivability. It was a 60% increase in raw output achieved through a weekend of labor and a handful of discarded parts. The hybrid small block was now punching in a completely different weight class. Its power figures were comparable to the massive 7-liter big block V80S that dominated the muscle car scene, yet it lacked the immense physical weight of those engines. While competitors were struggling with heavy iron blocks that ruined their cars' handling and weight distribution, Crower's 1955 Chevy possessed a power-to-weight ratio that allowed it to embarrass factory-backed machines at every stoplight. The discrepancy between the cost and the capability was the most disruptive element of the build. Professional racing teams were spending thousands of dollars on exotic manifolds and custom machining to find tenth-of-a-second improvements. Meanwhile, a teenager with a fundamental understanding of thermal efficiency was reaching the same performance ceiling by rummaging through a junkyard. This project proved that horsepower was not a luxury reserved for the wealthy. It was a reward for those who understood how to manipulate cylinder pressure and port velocity. Crower had successfully bypassed the entire automotive economy to create a giant killer, the sleeper that broke California. The ultimate testing ground for this technical heresy was a primer gray 1955 Chevrolet sedan. It was the quintessential sleeper, an unassuming grocery getter that looked like it belonged in a high school parking lot rather than the staging lanes of the Southern California underground racing scene. The car lacked the chrome, the custom paint, and the exotic badges of the high-dollar machines it lined up against. To the unsuspecting eye, it was just another old Chevy, but under the hood sat the hybrid engine that was about to dismantle the hierarchy of the street. As the primer gray sedan began consistently gapping cars that had thousands of dollars in professional work, the racing community spiraled into paranoia. Competitors who had spent small fortunes on aftermarket parts could not reconcile the car's performance with its humble appearance. They began inventing excuses to explain away their losses, fueling widespread rumors that Bruce Crower was cheating. Critics claimed he was hiding a secret nitrous oxide system in the trunk, or that he had somehow backdoored experimental factory parts from a high-level contact at General Motors. The reality was far more disruptive to their egos. There were no hidden bottles and no corporate favors. It was simply a junkyard special, beating deep pockets through superior engineering. Crower had proved that a sophisticated understanding of engine physics could effectively circumvent the need for a massive budget. This performance gap sparked a technical revolution in the streets, as racers realized that 500 horsepower was now accessible to anyone with a socket set and a map to the nearest salvage yard. The aura of the 55 Chevy transformed from a curiosity into a legend, proving that ingenuity was the most dangerous component on the road. Detroit finally catches up. The ultimate proof of Bruce Crower's brilliance did not come from a time slip at the drag strip. It came from the very corporate headquarters that had previously ignored the efficiency gap. By 1970, General Motors could no longer ignore the performance being extracted from their hardware by independent builders. Their response was the release of the legendary LT1 350, an engine that many historians view as a direct white flag to the garage-built hybrids of California. After years of strangling the 350 block with conservative designs, Chevrolet finally adopted the exact blueprint Crower had pioneered. The technical specifications of the 1970 LT1 were a mirror image of the Junkyard Special. It featured a high 11, 1 compression ratio, big valve iron heads with 64cc chambers, and a mechanical lifter camshaft. By pairing the long stroke of the 350 with the thermal efficiency of the 64cc chamber, GM was essentially mass-producing the Crower recipe and offering it with a factory warranty. They even topped it with an aluminum intake manifold and a massive Holley carburetor, legitimizing the high-velocity, high-compression philosophy that had once been dismissed as street racing heresy. While the factory officially rated the LT1 at 370 gross horsepower, this figure was largely a product of corporate politics and insurance industry maneuvering. Underneath the conservative rating sat an architecture designed for raw power. GM had to maintain an internal hierarchy, where the small block did not overshadow the flagship big blocks. But anyone with a wrench knew the truth. The kid in the garage had out-engineered the giants, forcing a billion-dollar corporation to follow his lead. The LT1 was not just a new engine, it was a formal validation that the thinking man's racer had been right all along. The danger of modular mixing. While the small block Chevrolet architecture was essentially a high-performance Lego set, mixing these generations required more than just a wrench. It demanded a master machinist's precision. To appreciate what Bruce Crower achieved, one must look at the other factory hybrids of the era. Chevrolet had already experimented with these permutations, creating the high-screaming Trans Am 302 by pairing a large 4.00-inch bore with a short 3.00-inch stroke. At the other end of the spectrum sat the 307, a sluggish economy engine that combined a small bore with a longer stroke. Crower's hybrid was the third and most aggressive logical permutation, but it faced a significant technical hurdle, the 1968 journal shift. That year, Chevrolet increased the main crankshaft journal sizes from 2.30 inches to 2.45 inches. This meant that parts from earlier 327S and later 350S were no longer a direct physical match without careful consideration of the reciprocating assembly. Furthermore, the 327 double hump heads often featured massive 2.02-inch intake valves. When these were bolted onto a 350 block with its 3.48-inch stroke, the margin for error vanished. The primary danger was catastrophic piston-to-valve contact. Without the correct clearances, the valves would slam into the piston tops at high RPM, turning a high-performance dream into a metallic grenade. Crower had to use his machining expertise to cut specific valve reliefs, often called eyebrows, into the 350 pistons to accommodate the larger 327 valves. This was the difference between a junkyard hack and a professional build. Many amateur racers who tried to copy the Crower recipe without addressing these clearances ended up with a pile of scrap metal. Crower's success was rooted in his ability to navigate these invisible mechanical boundaries, proving that true power was found in the details of the machining, not just the selection of the parts. From salvage to super empire, the success of the 1969 hybrid was more than a local racing victory. It was the foundational moment that transitioned Bruce Crower from a neighborhood mechanic into an industry titan. This discovery proved that the factory was not the final authority on performance, and with that realization, Crower Cams and Equipment was born. He recognized that while his head swap had conquered the problems of compression and airflow, the next frontier lay in the valve train. If he could optimize how the engine breathed, he could move past the limits of cast iron salvage and into the world of elite engineering. His company began pioneering technologies that would eventually become the backbone of professional racing. Crower moved from scouring junkyards to developing billet camshafts, lightweight titanium connecting rods, and high-performance roller lifters. These were not just parts, they were precision instruments that allowed engines to spin faster and last longer than anything previously imagined. His innovations eventually caught the eye of racing legends like Don Garlits, and his designs began influencing everything from NHRA Pro Stock to the high-stakes world of IndyCar. By 1985, the Crower catalog had ballooned to over 900 individual parts. Despite the scale of his success, the core philosophy remained unchanged. He was still the thinking man's racer who believed that if you thought hard enough, the answer would eventually come. He was still using existing physical principles to solve complex problems. Only now, he had the resources to manufacture the solutions from scratch. Crower had successfully scaled his junkyard mindset into a global empire, proving that the same brain that hacked a Briggs & Stratton at age 13 could redefine the limits of American speed. Capturing the hidden fire. Bruce Crower's intellectual curiosity did not stop with the small block Chevrolet. Decades after the 1969 hybrid discovery, his obsession with thermal efficiency evolved into something far more radical. In the 1990s, he pioneered the design for a 6-stroke internal combustion engine, an invention that fundamentally challenged how we view energy loss. While the rest of the world looked at a running engine and saw heat as a nuisance to be managed by radiators and cooling fans, Crower saw it as untapped potential. The concept was brilliant in its simplicity. After the standard 4 strokes, intake, compression, power, and exhaust, Crower added 2 more. Instead of moving immediately back to the intake cycle, his engine injected a fine mist of water directly into the scorching cylinder. The residual heat from the combustion process was so intense that it caused the water to flash boil instantly into steam. This rapid expansion of steam drove the piston down for a second, carbon-free power stroke. By the time the 6-stroke pushed the steam out of the exhaust, the cylinder was naturally cooled, and the engine had extracted work from energy that would have otherwise been wasted as heat. This invention was the ultimate second-order insight that defined Crower's entire career. The same principle that made his 1969 hybrid so effective, harnessing higher cylinder pressures and thermal efficiency, was now being pushed to its logical extreme. He realized that heat was not merely a byproduct of power. It was power itself. Whether he was bolting salvaged heads onto a block in a California workshop or reinventing the thermodynamics of the internal combustion cycle, his goal was always the same. He looked at the physics of the engine and found a way to make it work harder, proving that the most efficient engines aren't just built with bigger parts, but with better ideas. The Brotherhood of Speed. The success of Bruce Crower was not an isolated event. It was the high water mark of a mid-century American phenomenon where teenage engineering consistently humiliated the corporate status quo. Crower belonged to a loose brotherhood of speed, mechanics who lacked deep pockets but possessed a dangerous grasp of physics. One such contemporary was Gale Banks, who at 17 years old decided that a standard Chevy Nova inline 6 was not a grocery getter but a platform for forced induction. Using $60 in salvage parts and literal HVAC ducting, Banks scavenged a turbocharger from a Caterpillar diesel engine and bolted it to his Nova. The result was a 400 horsepower giant killer that obliterated expensive big block competitors, eventually launching his own engineering empire. In Detroit, Frank Moretti was running a similar play by exposing the horsepower lie of the muscle car era. While his peers were obsessed with peak power numbers on a dynamometer, Moretti focused on the integration of parts and torque multiplication. By utilizing internal velocity stacks to smooth airflow and calculating precise gear ratios, he made a 350 horsepower Chevelle SS consistently outrun cars with significantly higher ratings. Moretti understood that a high horsepower number was meaningless if the engine couldn't breathe or the drivetrain couldn't apply that force to the pavement. These young men proved that the industry's reliance on massive displacement was a crude solution to a refined math problem. They represented an era where the smartest kid in the garage was more influential than the biggest budget in the boardroom. The blueprint of modern performance. The technical DNA Bruce Crower established in 1969 is not a relic of the past. It is the foundation of the modern horsepower revolution. The principles he exploited to humiliate big block racers, high compression, high port velocity, and optimized quench, are the exact pillars upon which the current General Motors LS and LT engine series are built. Crower's most significant contribution was perhaps the mastery of the quench area. When his flat-top pistons traveled toward those small 64cc chambers, they squished the air-fuel mixture toward the center of the cylinder with violent force. This created extreme turbulence, which allowed for a faster, more homogeneous burn that prevented the engine from self-destructing. This is why he could run 11, one compression on street fuel without catastrophic detonation. Today, modern LS engines use sophisticated combustion chamber geometry to push this effect even further, running compression ratios as high as 11.5, 1 on standard pump gas. Every time a modern car owner enjoys high-performance efficiency, they are experiencing a direct evolution of the discovery made in a California garage decades ago. The spirit of the $35 trick is most alive today in the junkyard LS movement. All over the country, enthusiasts are pulling 5.3-liter or 6.0-liter iron truck blocks from salvage yards and pairing them with high-performance 799 or 243 casting heads. These builders are achieving 600 to 1,000 horsepower for a fraction of the cost of a factory crate motor. They are hunting for specific casting numbers and mixing components from different families of the same engine architecture to find hidden power. If you are currently in your driveway bolting a set of high-flow heads onto a salvaged truck block, you are walking a path that Bruce Crower blazed. He proved that speed is a matter of intelligence over income, and that the best performance parts in the world are often hiding in plain sight under a layer of grease and rust. Wisdom over wealth, success. The 1969 hybrid engine was far more than a triumph of cast iron and compression. It was a cultural turning point that shattered the class system of the automotive world. Before this discovery, the common consensus was that massive power required massive investment. Speed was seen as a luxury item reserved for those who could afford the latest factory performance packages or expensive aftermarket catalogs. Bruce Crower dismantled this logic, proving that a teenager with $40 and a fundamental understanding of fluid dynamics could out-engineer a billion-dollar corporation. This shift moved the barrier of entry from deep pockets to deep knowledge. Bruce Crower maintained that his greatest innovation was not a camshaft or a cylinder head, but a specific way of thinking. His mantra to question everything and try the impossible became the guiding light for a generation of mechanics. This philosophy turned the garage into a laboratory and the junkyard into a library. It fostered a spirit of open-source engineering, where the sharing of secrets and casting numbers became the ultimate currency. Speed was no longer a commodity to be purchased. It was a reward for those willing to observe, experiment, and ignore the conventional wisdom of Detroit. This era represented a high-water mark for mechanical liberty, before the restrictions of the mid-1970s took hold. For a brief moment, the smartest person in the room was the one with the dirtiest fingernails. Crower's legacy is the realization that ingenuity is the most valuable component in any engine. He democratized speed by proving that the laws of physics do not care about your budget. If you understand the math and respect the mechanics, you can build a giant killer in your own driveway. The thinking man's final victory. The legacy of Bruce Crower's 1969 discovery is defined by 3 pillars that changed automotive history: mechanical optimization, economic disruption, and corporate influence. By identifying that a smaller, high-velocity combustion chamber was superior to a large, lazy one, Crower didn't just build a fast car. He provided a blueprint that forced Detroit to rethink its own engineering standards. He shattered the price barrier to elite performance, proving that 510 horsepower was not a luxury for the wealthy, but a result of understanding the laws of physics. The true magnitude of this achievement becomes clear when contrasted with the era that followed. Just 6 years later, the mid-1970s smog era arrived, forcing compression ratios down to a pathetic 8.2, 1 and dropping engine output to a mere 165 horsepower. Crower's hybrid stood as the high water mark of the golden age, a peak of efficiency that the industry would take decades to reclaim in a street-legal package. It serves as a reminder that the best engineering solution is rarely the most expensive one, but the one that most elegantly aligns with thermal pressure and port velocity. The $35 trick was never a simple mechanical hack. It was a masterclass in independent innovation. It remains a permanent testament to the idea that ingenuity is the most valuable component in any engine. Bruce Crower proved once and for all that a thinking man with a wrench will always be more dangerous than a man with only a checkbook.